In 13.7, we're going to look at motion in 2- and 3-dimensional space. So we're going to revisit our familiar position, velocity, speed, and acceleration. But this time our position function is going to be a vector. So the velocity is the same as real valued function. Velocity is the derivative of the position vector. So the velocity is also a vector. Speed is the magnitude of the velocity. And acceleration is going to be the derivative of the velocity, which would be the second derivative of the position function. So again, this is all very familiar to us. Let's look at example 1. We want to find the velocity, speed, and acceleration of the object that's defined by this position function r of t. So the velocity function is simply the derivative of r, which would be 1 minus 2t, 4, and 6. So this would be our velocity function. The speed would be the magnitude of our velocity function. And there's our roosters. Oop, I forgot my arrow over my velocity function. So that's going to be the square root of 1 minus 2t squared plus 4 squared, or 16, plus 6 squared, or 36. Multiplying all of this out, I'll end up with 1 minus 4t minus 4t squared. So that would be the square root of 4t squared minus 4t, and then 16 plus 36 plus 1 would give me 53, plus 53. So this is my speed. Excuse me. And then the acceleration is simply the derivative of the velocity function. So again, this is going to be a vector. It would be -2, 0, 0. We're going to discuss two types of motion, common types of motion. One would be movement in a straight line, and the other is going to be circular motion. So we're not going to do much with this. We're just going to talk about this. So when we talk about straight line motion, so we have this trajectory, and it's given by this vector valued function, but if you notice the components are all linear. We have an x sub 0 plus at, which is linear, and the same for the y and the z components. The initial point is some x, y, z naught, and then we have our direction vector ABC. So the velocity is going to be the derivative of the position function, and the acceleration is the derivative of the velocity. So that's just movement in a straight line. R is linear. So we're going to move on to circular motion, and again, this is all super familiar to us. Again, this is 2-dimensional. We're not in 3-dimensional space yet. So 2-dimensional circular path of any object, and here we're assuming that the circular path has a center at the origin. So we can write it as the 2-dimensional vector A cosine t, A sine t, where A is just some constant, and that would be similar to an r value, a radius value, but we don't want to use r because that's what we've named our function. So you get the whole path if you go from 0 to 2 pi. Velocity is going to be the derivative of r, and acceleration is the derivative of velocity. So it turns out that in a circular path, your acceleration is going to actually be negative position function. And that's what's in this diagram here. So if you take your vector, your position vector, and again, the tail is at the origin, so the head is going to give you points on your circular path. So here our circular path is actually being generated counterclockwise, right? So as we go around, our R value just gives us different vectors whose head will be any point on our circular path. Well, when you take the derivative, what you get is you get your velocity vector. And whenever you take the derivative, you get a tangent vector. So if this blue vector is r, then the velocity vector is going to be this tangent vector. And it's going to be going in the direction that the path, the circular path, is generated. So in this case, counterclockwise. And then when you take the derivative of your velocity vector, you're going to get this acceleration vector that's going in the opposite direction of r. So if you look at r and a, they're both orthogonal or perpendicular to our velocity vector. So remember that when you take the dot product of vectors that are orthogonal or perpendicular, their dot product is going to be 0. So if you dot r with v or a with v, you should get 0. Oh, that was a loud one. What we're really interested in is not so much the straight line movement or circular movement in two-dimensional space, because we've talked about that a whole bunch. What we're really interested in is motion in three-dimensional space. So the first thing we're going to look at, and we're going to explore this more in later sections, is we're going to look at motion where the magnitude of r is a constant number. So r is going to describe a path where its magnitude is constant. So this is going to be motion on a circle or a sphere. So when we take r dotted with velocity, we're going to get 0. And this diagram here is what we're talking about. Remember, this is in three-dimensional space. So if we look at these vectors r, as time goes on, r moves in the same direction as this circular path. But notice that this circular path is no longer in the xy plane, it's just in space. And at each point we have what we had in the two-dimensional motion, we have these velocity vectors that are orthogonal to r. But it turns out that the circular path is this path along a sphere. Okay. So that's how we would describe that three-dimensional circular path, as a path along a sphere of radius r. In example 2, what we're going to do is we're going to verify that the trajectory that we have here, r of t equal to 4 cosine t, 5 sine t, and 3 cosine t, is a sphere centered at the origin. And we're going to describe our trajectory. So to verify that it's a sphere with center at the origin, just remember that the equation of a sphere with center at origin is x squared plus y squared plus z squared equal to the radius squared. And here I'm going to use r not as the position function, as radius squared, which is why I don't have the vector arrow on top of it. So that's just the general equation of a sphere with the center at the origin. So if we look at our function r, we could look at the first component as being our x, second as our y, and the third as our z. So all we have to do is verify to see if we do x squared, which is 4 cosine of t squared, plus y squared, which is 5 sine of t squared, plus the z squared, which would be 3 cosine of t squared, We just want to make sure that that's going to be equal to some r squared. Okay, so we get 16 cosine squared theta plus 25 sine squared theta plus 9 cosine squared theta, and combining the cosines, we get 25 cosine squared theta plus 25 sine squared theta. Factoring out the 25, cosine squared plus sine squared is just 1. So this is equal to 25. And that's verification enough to know that the equation is x squared plus y squared plus z squared equal to 25 would be our r squared. So in this case, our radius would be 5. So we verified that this describes a sphere. So the next thing we're going to do is we're going to find the position and the velocity vectors, and then we're going to show that they're orthogonal by taking their dot product. Hopefully it'll be equal to 0. So my velocity vector is going to be equal to -4 sine t, because I'm just taking the derivative of r, 5 cosine t, and then -3 sine t. Now when we take r and we dot it with v, remember that means multiply, add, multiply, add. So it's going to be equal to -4 sine times 4 cosine. So it's going to be a -16 sine cosine plus, we'll get a 25 sine cosine and then a -9 sine cosine. So notice these are all like terms. When I add them together, I get 0. All right, so we have this circular path. It's centered at the origin, but we haven't talked about how it's generated. So it's generated counterclockwise. And it has a radius of 5. So usually in three-dimensional space, we don't talk so much about the way it's generated. It's enough for us to say that it's a sphere, it has radius 5, and its center is at the origin. So that's enough. So the next thing we're going to talk about is acceleration and our position functions. And this is the same thing that we did in Calculus 1, Calculus 2, is if we have acceleration, then to get to our velocity, we integrate. To get to position, we integrate. Example 3, we have the acceleration vector as 1, 3. The initial velocity, u sub 0, v sub 0, is the vector 1, 1. So this would be v of 0, the initial velocity. So we're assuming that happens when t is equal to 0. And the initial position, x sub 0, y sub 0, is the vector 2, 3. So that's going to be r of 0. So we're supposed to find the velocity and the position vectors. Our velocity vector is going to be the integral of our acceleration, which is 1, 3, with respect to t. That gives us a vector. It's going to be the vector t, 3t. But remember, we have to solve for our constant vector. And that involves that initial position, or the initial velocity. So the initial velocity is the vector 1, 1. Which means that at t is equal to 0, which gives us the vector 0, 0, plus c, we know that that has to equal the vector 1, 1. Which tells me that my constant vector c is equal to the vector 1, 1. Our velocity vector is now the vector t, 3t plus 1, 1. And oftentimes in my math lab, they will leave it as the addition of two vectors. But the nicer way to write it is to combine these to be the vector t plus 1, 3t plus 1. So we found our velocity vector. The next thing we have to do is find our position vector. So I'm going to go back up and find my r of t, which is just the integral of v of t. So that would be the vector t plus 1, 3t plus 1. Again, we're integrating component-wise, so the integral of t plus 1 is t squared over 2 plus t. Comma 3t squared over 2 plus t, and then plus a constant vector. Our initial condition is that r of 0 is equal to the vector 2, 3. So if I substitute in 0 for t, that will give me my constant vector equal to the vector 2, 3. So at last I have my position function, vector value function, as, if I add all of those together, 1/2 t squared plus t plus 2, 3/2 t squared plus t plus 3. The next thing we're going to talk about is two-dimensional motion in a gravitational field. So when we say gravitational field, what we're going to assume is that the only force acting upon our object is the force of gravity. So using Newton's second law of motion, we have that mass times acceleration is going to be the sum of all the forces. Now let's look at this diagram. Let's say that we have this trajectory, and that would be this curve in black. And now the initial position does not have to be at the origin. In this diagram, our initial position is some r of 0. And we'll call that x sub 0, y sub 0. So at that initial position, we're going to have our initial velocity, v of 0, which we'll call u sub 0, v sub 0. Since the only force acting upon our object is gravity, our force vector is a downward vector, which would be 0, comma, negative mass times gravity, or negative mg. And now here, since this is gravity, remember with gravity it could be either 9.8 meters per second, so that's if we're in metric, or we could use gravity equal to 32 feet per second squared. Sorry, I forgot to put my square on here. Seconds squared. So we have this downward force. And I would just like to double check these properties in the summary. So down here in the summary, we're looking at two-dimensional motion with some initial velocity that we've already talked about and some initial position. So to compute the velocity vector, you don't have to go through all this, take the derivative of r. The velocity vector is simply going to be the u sub 0, and then it's going to be negative gravity times t plus v sub 0. And the position vector, if you have all these initial values, is going to be the vector u sub 0 t plus x sub 0, that's our first component, plus negative half gt squared plus v sub 0 t plus y sub 0. And so that is if the only force acting upon it is gravity. What I'd like to do is just verify that that's our velocity vector, and then the similar verification would be for our position vector. So mass times acceleration is going to be equal to the sum of all our forces. But since gravity is the only force acting upon our object, I can write the sum of all forces as 0, negative mass times gravity. And then on the right-hand side, I could factor out mass. So this is nothing that you have to replicate. It's just nice to be able to verify things. Notice in this equation I have mass on both sides, and it's the same mass, so I could just cancel that off of both sides. I end up with acceleration, and here I keep forgetting to put my arrows on my vectors. So fired. So the acceleration vector is equal to 0, force of gravity, which means the velocity vector, as I forget my arrow, is going to be equal to the integral of 0, negative gravity and that's going to be equal to 0 times t, so 0, negative g times t plus our constant vector, and our initial velocity v of 0 is u sub 0 v sub 0, so I can replace this constant with u sub 0 v sub 0. And that gives me our velocity vector as the vector u sub 0, negative g times t plus v sub 0. Okay, so all I wanted to do was verify that this was true, that this is how I can define my velocity vector. And then by the same argument, we can go ahead and integrate our velocity and get our position vector. Let's apply this idea to a baseball hit from 3 feet above home plate. So it has initial velocity, and in this case the velocity is in feet per second. So if the velocity is in feet per second, then the gravity that we're going to be using is 32 feet per second. So we have this initial velocity, and this is two-dimensional space, so it's 60, 60. Gravity is the only force acting upon this ball. Part A says find the position and the velocity of the ball from the time it's hit to the time it hits the ground. Now, sometimes it's nice to see a little diagram. So this ball is being hit at 3 meters above the ground. It's going to go up and then it's going to come down. Well, maybe I'll make this a little bit longer at some point here. So we have this initial velocity vector in red. And now for part A, I'm going to be using the acceleration. Since it's gravity is the only force acting upon this object, the acceleration is going to be the vector 0, comma. Gravity in this case is 32, so remember it's negative gravity. And I do have that my initial position is 3 meters, or I'm sorry, it should be 3 feet. 3 feet above, I'm so used to working with meters, above the ground. So this is going to be 0, the vector 0, comma 3. And then I also know that my initial velocity is the vector 60, 60. So I have all this information. I'm supposed to find my velocity vector, so I'm just going to go ahead and use that formula on the other page. Our u sub 0 is 60, comma, this is going to be negative gt, so negative 32t, plus v sub 0, which is 60. And I'm done. I've got my velocity vector. And my position vector from the formula on the other side is going to be 60t, comma, negative 32t squared over 2, so it's going to be a negative 16t squared, plus 60t plus 3. And that was part A. Part B, we're supposed to see how far the ball travels horizontally. So we're going to be finding this distance here along the x-axis for part B. Well, first of all, I have to know when the ball hits the ground. And it's going to hit the ground when its height is 0. Let's go back to our position function. The first component, 60t, that would be our x value. So it's a function of x. The second component, negative t, 16t squared plus 60t plus 3, that's going to be our y value. So when this y value is equal to 0, and that's when the ball is going to hit the ground. We just have to solve the quadratic equation, negative 16t squared plus 60t plus 3 equal to 0. I don't believe this factors. So if you use the quadratic equation or you simply plug this in a calculator, when I did, and I'm going to go 1 decimal place, my t values are approximately 3.8 seconds. So at approximately 3.8 seconds, that's when this object is going to be on the ground. So all I have to do now is look at the x function, 60t, because that will give me my x value, which would be this distance along the ground, and compute x of 3.8, which is going to be 60 times 3.8. So I have about 228 feet. So that would be the distance that that ball has traveled horizontally. Now when we look at part C, it says, what is the maximum height of the ball? So this is a parabola. We could simply find its vertex from algebra, and it'll give us the maximum height. But I don't want to do it algebraically. This is a calculus class, so I want to think about this in terms of calculus. If we go back to our derivative, we notice that at the vertex, that's when our velocity vector is 0. Because the velocity vector is the derivative of the position vector. So we're going to have a maximum height when the velocity is 0. But the velocity vector is made up of two components. It's made up of a x and a y. So it's actually going to be setting the y component of the velocity vector equal to 0. Okay. So it's when this is equal to 0, but we're just looking at the y component. Which would be the negative 32t plus 60, set that equal to 0. So minus 60 divided by negative 32. I have that at t equal to 60 over 32, which I don't have to round, 1.875. So at 1.875 seconds, that's when this object's going to hit its maximum height. But to find the maximum height, I have to put this t value back into my position function because I need to find the y value, since that's going to correspond to height. So when I'm looking at the maximum height, it's going to happen when t is equal to 1.875 seconds. Which means I'm going to evaluate the y component of the position vector. So the y of t. Which is simply negative 16, 1.875 squared, plus 60 times 1.875, plus 3. So we get 59.25 feet. That would be the maximum height. Again, you could have just used your algebra and looked at the quadratic of the position function, found the vertex by first doing negative b over 2a, and then plugging it back in to get the height. So in this next box, we're going to look at what we call range, time of flight, and maximum height. We're still in two-dimensional space here. Now this idea of time of flight is simply how long an object has been in motion or in flight. This range is going to be the distance from start to end horizontally. And then the maximum height would be the usual maximum y value height. To use these formulas for time of flight, range, and maximum height, you must have an initial position at the origin. So in this particular summary box, it's only dealing with an object that starts off at the origin. So we could not use this in our last example because our baseball was hit at a height of 3. Example 5 says a rocket is fired at an angle of 60 degrees above the horizontal with a speed of 200 meters per second. So that tells me that gravity is going to be the 9.8. Find the position and the velocity vectors, determine the time of flight and range of the rocket, determine the maximum height of the rocket. Let's look at part A. Well, our initial velocity we don't have that vector. The most I can say is it's fired at an angle of 60 degrees. And I know the speed, so remember the speed is the magnitude of our velocity vector. So since I have an angle and I have a magnitude, what I'm going to do is go back to writing our vector in terms of the trig function, which would be the cosine and sine. So this becomes the vector 200, cosine of 60 degrees, comma 200, sine of 60 degrees. That gives me the vector, so this is just the initial velocity now. Of 100, cosine of 60 is half, right? So that would be 100, comma 100 square root of 3. So I have my initial velocity. Also note that my acceleration since the only force acting upon this rocket is gravity, and I'm in meters, it would be the vector 0, comma, negative 9.8. So what about my initial position? The rocket is launched at ground level, so my initial position is 0, 0, which is what I want because now I can use what's in this summary box. If I have to determine the time of flight and the range, well, the time of flight, actually let's find our velocity function. My apologies, which would be v of t equal to 100, because that would be the u sub 0. And then we're going to have negative gravity, 9.8 t, plus the u sub 0, which would be 100 square root of 3. So we could use the definitions that we had before with the velocity and our position vectors. So our position vector r of t is going to be 100t, comma, negative 9.8 t squared over 2, which would give me a negative 4.9 t squared, plus 100 square root of 3t, plus 0. Because that was our initial position. Using what's in the summary box, the time of flight, which we're going to let be this capital T, that's how long the object has been in flight, is going to be 2 times the magnitude of the initial velocity, and the magnitude of the initial velocity was 200, right? That would be its initial speed. And then sine of 60, which would be the square root of 3 over 2. So all I'm doing is just plugging things into my formula over gravity, which is 9.8. And here we're not doing a negative gravity, we're just doing 9.8 positive. So when I plug that into my calculator, I'll go 1 decimal place. I get 35.3 seconds. So that's how long the object has been in flight, or its time of flight. Now its range is going to be equal to its initial velocity squared. So that's going to be 200 squared times sine of 2 times 60, so it's going to be sine of 120 degrees, divide that by gravity, and again, just plugging this in a calculator, I get 3534. We'll go 1 decimal place. You notice I rarely use significant figures. So 3534.8, double check me on that, meters. That's that horizontal distance that it's traveled. And then part C, we're supposed to determine the maximum height of the rocket. So that's going to be the maximum height in that box there. Again, remember, we can only use these formulas if our initial position is 0, 0 at the origin. This is going to be y of time of flight over 2. So our time of flight was 35.3 over 2. So that's what we're putting in the y component of our position function. So wherever we see t, we're going to replace it with 35.3 over 2. That's going to give me negative 49. 35.3 over 2 squared plus 100 square root of 3 times 35.3 over 2. And again, I'm just going to plug that into my calculator to get 1530.6 meters. So that would be the maximum height of this object. So let's finally talk about three-dimensional motion. In this box, it says if the only force is gravity, then our force vector is going to be the vector 0, 0, negative mass times gravity. But since the only force is gravity, then that's our acceleration vector. We can write that as 0, 0, negative gravity. If gravity is not the only force acting upon our object, if we have other acceleration forces, then we're just going to add those forces to our acceleration. If you look at the diagram, you could see that the acceleration is this downward force, pulling our object down. So again, we're in three-dimensional space. The problem is when we're in three-dimensional space, things get a little bit more complicated mathematically. So you notice that there's no formulas besides acceleration. There's no formulas in here when we talk about time of flight, range, or maximum height. Also, something you should notice is that nowhere in there does it say that the initial position has to be at the origin. So what we're going to talk about here does not require, and we're going to talk about our time of flight, range, and maximum height. Doesn't matter if the initial position is not at the origin. That only matters in our last summary box in 2-dimensional space. 3-dimensional space, we're just going to talk about these ideas, and then we're going to kind of figure them out based on this application that we're going to look at. So time of flight, that's going to be the time when our object returns to the ground. So when you think about the object landing on the ground, that's when your z value of your position vector r is 0. Now the range is going to be the distance traveled, which is going to be the magnitude of the position vector at the time of flight. So notice there's no formula here, we're just talking about what it means in words. The maximum height is when the z component of the velocity vector is 0. Now let's go ahead and apply it in this example here. So we have this soccer ball. It's kicked from the point 0, 0, 0. Okay, so that makes sense because soccer balls are usually in play at ground level. So the initial velocity is this vector 0, 64, 64, and it's in feet per second. So here's something tricky. The spin on the ball produces an acceleration of 0.800 feet per second squared. So that's another force acting upon our object, and it's an acceleration force. So when we figure out total acceleration, we're going to have to take the force of gravity and we're going to add spin. So remember, when we talk about forces acting upon an object, we add all the forces together, and that gives us the total force that's acting upon an object. Okay, part A says find the position and velocity vectors. Well, first of all, my acceleration vector is going to be the spin, which is the vector 0.8, 0, 0. And I'm going to add it to the force of gravity, which is the vector 0, 0, negative 32, since we're in feet. And that gives me an acceleration vector of 0.8, 0, negative 32. So I have this acceleration. This is our total acceleration because we had to add spin. All right. My velocity vector occurs when I integrate my acceleration, 0.8, 0, negative 32, with respect to time. And I'm just going to work across. That's going to be the vector 0.8 t, 0, and negative 32 t, plus my constant vector. Well, when t is equal to 0, the initial velocity is going to be the vector up above here in the problem. It's going to be the vector 0, 64, 64. So that tells me that c is going to be equal to 0, 64, 64. So we look at our velocity vector, and adding in that 0, 64, 64 component-wise, this is going to be the vector 0.8 t, comma 64, comma negative 32t plus 64. I have my velocity vector. Now I'm going to find my position vector r by integrating my velocity vector. Okay, with respect to t. And that's going to be equal to, I'll just go across, 0.8t squared over 2 is going to give me the vector 0.4t squared, comma 64t, comma negative 32t squared over 2, so negative 16t squared plus 64t plus my constant vector. Okay, now remember that my initial position was the point 0, 0, 0. So that tells me that my initial position is this vector 0, 0, 0, which also tells me that that's my constant vector c. So my position function is simply the vector 0.4t squared, comma 64t, comma negative 16t squared plus 64t. That's part A. Let's look at part B. Part B says to determine the time of flight and the range of the ball. Well, the time of flight is going to happen when the z component is equal to 0. So that's when negative 16t squared plus 64t is equal to 0. I don't have to do quadratic. I can simply solve this by factoring to get 16t times negative t plus 4. So all I did was pull out a 16t. And then that gives me 16t is equal to 0, or t is equal to 0, and negative t plus 4 equal to 0. So t is equal to 4. So when t is equal to 0, hasn't left the ground. So the time of flight must be the 4 seconds. So time of flight is 4 seconds. And now if I take the magnitude of my position vector at 4 seconds, I'm looking at the magnitude of the vector. Remember, we're putting 4 in for t into the vector. Let's see, 0.4 times 16 in a calculator. That gives me 6.4, comma. 4 in for t and 64t gives me 256. And if I put 4 in for the z component, I just get 0. The magnitude here is simply the square root of 6.4 squared plus 256 squared. Take the square root. In a calculator, it's about 256.1. So about 256 feet. The range is approximately 256 feet. Part C, we're supposed to determine the maximum height of the ball. So the maximum height of the ball occurs when velocity is 0, but we're only concerned with the z component because that has to do with height. So all I have to do is set negative 32t plus 64 equal to 0. Oops. And solve for t. I get t is equal to 2 seconds. So that's when we have maximum height. But again, remember the maximum height is going to occur for the z value of the position function. So we're going to have a max height when negative 16 t squared, where t is 2, so negative 16 2 squared plus 64 t, so 64 2. So when we compute this, we get 64, and the units are feet, and that's when we have our max height. So this is just exploring acceleration, position, velocity in terms of vectors in both 2 and 3-dimensional space, and sort of introducing this idea of motion. That's it for this section.